Hello students, welcome to Young Cubs and we are continuing the chapter of electricity. Today will be the day 4. We will learn about the different types of connections so that electricity can be utilized in a maximum way. But however, how many types of connections can you do to make your device or appliance work? So the first type of connection is connection in series. What does connection in series means? A series of appliances are, placed or are connected back to back. So here we have a cell. Okay, this is connected via a wire to a bulb. Okay, and a little ahead, the wire is connected to another bulb. Okay, here the switch is closed and a complete round loop is formed. So if I add another bulb over here, even that will go. So the same path or the same wire contains a series of appliances for them to work. All right, let's take a few scenarios. Before taking different scenarios, children just want to make sure that all the symbols are very clear to you. All right, one big, one small, lines are known as the cell. Okay, the symbol of a bulb is like that. Okay, that's a simple wire. Okay, if you have a sleeping line between two dots, it's a closed switch. And if you have something like that, okay, it is an open switch. Many a times a bulb is denoted something like that as well. The wires here, a glowing bulb like that. All right, children, easy. So let's see what happens to the appliances in connection in a series connection and a series circuit. Okay, now I will be drawing only only symbol diagrams, only symbols, diagrams with symbols. Okay, here we have the cell. Okay, I'm making the switch, closed circuit. Okay, here I've attached one bulb, second bulb, and here I complete the circuit. Okay, the wire is continuously flowing. Yes, children. Hence, the bulbs will glow. Both the bulbs will glow. Now, if I add another bulb, okay, if I add another bulb to this circuit, alright, what happens? The bulbs will glow, but they will comparatively be a little dimmer. So any further appliances or any further, bulb or buzzer or a motor added to this connection, okay, it will work, but the power given to each of these appliances will go lower and lower. The power will decrease. The bulbs will be, over here will be dimmer, as compared to the bulbs here. All right, because the power is getting distributed. All right, children, do we understand this? Okay, now if I have the connection of the bulb, okay, in the circuit, okay, I have the connection. How do I denote it? I'll just show it like a open hook. Okay, I have the connection out here, but I've just brought out the bulb. Okay, I just have taken out the bulb of this. Okay, do you think this bulb will work? No. The circuit out here in the middle apparently is broken. Hence, this bulb will not work. So, in short, if you're connecting anything in this circuit, in the series circuit, what exactly happens is all need to be connected thoroughly. You cannot let the output of the appliance moved out, and you say, just go on with one bulb and we'll remove the other. Or if one bulb is fused, if I have this bulb out here, assuming that I have the bulb out here, but this bulb is a fused bulb, not working. The tungsten wire has broken, or some problematic because of which one bulb is not working. Do you think this one will work? No, it will not. All right, children. Okay, let's have one more scenario. Or if even for that matter, I'll just show it to you in this circuit only. If, for example, I have a breakage in wire. For some reason, the wire out here is broken or is not connected to the circuit. There is a gap out here. Electrons won't jump from here to here. Children, they don't jump. They don't skip. Okay, so the circuit, all in all, the circuit has to be complete. Okay, the fourth scenario is in case I attach two cells to the circuit and I have a single bulb. Okay, trust me, the bulb will be really brightly glowing. The moment I add another bulb out here, that is also going to be bright enough. If I had the third one out here, okay, this will also glow because I am giving more power. But however, the third bulb will, comparatively, the first one glowed really bright. The second one was bright. All three, if I added the second one, both the bulbs were still bright. But when I add the third one, all three will be dimmer. If I add the fourth one, they'll still be dimmer, and so on. So more the appliances, okay, the electricity gets distributed amongst all three. The more these cells, the brighter, the more the electricity passing through these appliances, and more the brighter the bulb, stronger the power going around the circuit. So understood, the connection, the series circuit. Okay, let's go to the next one. We have a parallel connection. What do you see in a parallel connection? you have a battery or a single cell, then each appliances have each of the appliance has a different pathway. So if the electricity is flowing like that, okay, this is a different loop that is formed. This is loop number 1, appliance number 1. Then this is loop number 2. Okay, this is loop number 1. This is loop number 2. Then this is loop number 3. So there are 3 different pathways, okay, and 3 different wires by which the appliances are connected. Now, what is the benefit of this? Okay, in series circuit, even if one bulb was removed, okay, the entire circuit wouldn't work. But here, for example, I eliminate this one. The other 2 bulbs will glow. Okay, that's the scenario with a parallel circuit. All right, even if one of the bulbs do not work, the other two keep glowing or keep working. In a series, what exactly happens is it can either all will work or none will work. Here, you can have different switches for each of them. So if I have a separate switch out here for this one, I want only this bulb to work. What I'm going to do is I'm going to keep this switch open, or I am going to switch off the bulb, say from here. And I can have the first and the third bulb working. Yes. So that's what happens when you get a choice. If one of these circuits, say, is broken, so if I draw this out here, so if here we draw a circuit, big one, small one, I have one bulb here, another bulb here, and the third one here. Alright, each one of them has a different pathway, an individual dedicated pathway. Alright, we can add switches. For each one separately. If each one does not have a switch separately, you don't want it that way, there could be a common switch. Okay, anything is possible, a lot of options. Okay, even if one of the bulbs does not work, the other 2 will work. Okay, it can be this can be individual, whichever is not working can be individually repaired. All right, children. So this is how parallel circuit is preferred over series circuit. All right. So here, parallel and series circuit. In a parallel circuit, the same terminals of both devices are connected together. Okay. In a series circuit, a series circuit is made by connecting the end of the device to the beginning of the other. So they have different connections out here. Do you get this? They have different connections out here. But whereas here, this one start, it ends over here. This is the start of the other one, and this is the end. Alright, children. So parallel circuits and series circuits are clear. Let's look at a detailed distinction between the two. The amount of current, so in series circuit, the amount of current that flows through all the load is the same. It's the same. The amount of electricity flowing through each appliance. The current flowing through each load combines to form a net current. Okay, everybody gets a separate set of electrons flowing through their individual paths. In an electrical circuit, loads are arranged in a line. In an electrical circuit, loads are arranged parallel to each other. The voltage across each resistor is different, V1 plus V2 plus V3. Here, so basically this adds up. Okay, over here, each one has its different resistor. So across each resistor is the same. So V1 will be equal to V2 and will be equal to V3 and so on. So you can have as many bulbs as possible. If one component breaks down, the whole circuit will burn out. Other components will function even if one component breaks down. The other components will function. Even if one component breaks down, each has its independent circuit. Alright, children, this is a detailed distinction. You can note it down. It is good for your exams or for your notes. Normally in the lower grades, okay, series and parallel circuits are more stressed upon. But since we have a lot to learn about electricity, it's just a part of this chapter by the time you come in the 8th and 9th grade. Okay, children, talking about earthing of appliances. The outer metallic body is connected to the earth wire. Why? So, children, what is the appliance? We can take up any appliance such as the refrigerator, oven, geyser, etc. Why is it connected to the earthing wire? The reason is that sometimes this wire which is getting connected inside. Okay, now assume there's this wire, okay, which apparently it has a, not here. So inside the appliance, okay, for example, obviously this wire is going inside. This wire is going inside, and if there is a breakage out here, okay, it has a breakage. Okay, this may touch the outer body. Okay, this outer part is made up of a conductor. This may be of an insulator, but this live wire may come in contact with the conductor part of it. So the conductor will now conduct electricity, and if you touch this device, you happen to get in contact with the open side or the open outer metallic body, it can give you a real shock, a fatal shock. Okay, if you touch this appliance, because there is some breakage inside and the live wire is coming in contact with the metallic body. Alright, so to avoid this, what do? They have, a 3-pin plug normally. You've seen it in your houses. They have like a triangular shape thing, okay, wire. So they have a 3-pin plug. Okay, wire 3-pin plug. One wire will be the live wire, the second wire will be the neutral wire, and the third wire, which is important to avoid these shocks. In case if the live wire comes in contact with the metallic body, the third wire, which is the earth or the earthing wire, is being put into such circuits only to protect us from fatal shocks. Okay, I remember I told you the electricity loves the ground, the earth. So if you become the medium to go down there'll be a fatal shock or or a very high current passing through your body, and you will get a current, or you'll get a shock. All right, children, it's just to protect us. So, what are short circuits and overloading? What is a short circuit? Circuit occurs when a naked live wire and a neutral wire come in contact. So when they come in contact, a live wire or a neutral wire, or the live wire and the earth wire, when they come in contact, okay, it's major. Okay, so what happens then? Okay, it may generate a lot of heat, and there's a short circuit which can occur. All right, a lot of heat can generate, and then you know that there could be a fire breakout in the house or wherever. Okay, what is overloading? Lots of electric current being passed. Okay, so overloading of an electric circuit is a condition when it draws more current than it is designed for. So if there's a lot of current passing through a circuit, okay, the circuit will heat up, okay, and there'll be overloading, and the whole circuit gets burnt. Okay, and that's where, for so that there's no overloading, what do we bring into the picture? We bring in MCBs, miniature circuit breakers, so that there's an electric cutout. Okay, then earthing is down in a house near the kilowatt hour meter. So earthing is done where? Okay, near the kilo, in energy meter. It's there where the meter is present. Okay, children. Now, children, we know about electricity, the circuit, the series circuit, the flow of electrons. We've done a lot. We've learned the components, then we've spoken about MCBs, everything. And we know that electricity is very useful. Now electricity is one of the basic needs of every individual. In India, apparently, this basic needs is thought of very critically, and is made sure by the government that it reaches every village, and everybody has 24/7 electricity. Okay, so it's one of the basic needs now. Now, hazards of electricity. Though it is very useful, we've just seen that how dangerous can it be. Yes, so let's go through a few hazards of electricity. Overhead power lines. The electric power lines usually have high voltage. We've seen that as well. Okay, 11 kilowatt to 132 kilowatt step up place and everything. Okay, now that can cause major burns and electrocution to workers while touching the cables out of their knowledge. So if they don't know that there's a cable out there, or they do have no knowledge about what's the kind of power the live wire is carrying, it can be dangerous, it can be hazardous for them. Now, using damaged tools. So when the electrician comes to repair a crack or any kind of wire, okay, and is unaware of the breakage, it can be really, really dangerous, and he can get a shock. So cracked wire, cables and cords result in high equipment damage and may produce electric shock while operating the device. So equipment damage, okay, if the tool is damaged, equipment damage, as well as electric shock to the person handling it. Inadequate wiring and overloaded circuits. So if the thickness of the wire is not enough, or there's an overload problem in the circuit, okay, or you use wires of the wrong size for connecting the circuit, it can cause overheating and fire. exposed to electric parts. If there's a breakage, or the live wire is exposed. Okay, it includes improper lighting, open power distribution units, and detached insulation parts on electrical cords, which causes potential shock and burns. Children, you know there's a pin plug, or there's a 2-pin plug also in your house. Okay, always handle them from this plug. Do not try to get in touch with the three what do you call pins, the 3 pins, because they are made up of metal, they're made up of steel. You can get a burn. Okay, improper grounding. Talking about the earthing, improper grounding highly increases the unwanted voltage and produces risk. Unwanted voltage and produces risk. Okay, by mistake. Okay, damaged insulation. While using damaged insulation, metal wires inside the cable get exposed. When a person touches the exposed wire, they could get an electric shock. Okay, and most important, operating electric equipments at wet locations highly increases. So water is a very good conductor of electricity, children. So if you're talking about distilled water, what is distilled water? Distilled water is, it has no impurities. That is a bad conductor of electricity, children. However, we do not use distilled water everywhere. So water basically has impurities, has various minerals in them, dissolved in them. Hence, it is a very good conductor of electricity. All right, children. This much understood. So, if it's a very good conductor of electricity, it is very easy to get a shock if you touch the devices, appliances with wet hands. This brings us to the do's and don'ts while handling electricity. Okay, what are the don'ts? Don't touch switches with wet hands. Don't try to repair any appliance while in use. So the fan is on and you're checking things. No, there can be anything. You can cut your hand, you can burn your hands while handling a high voltage tube light or a bulb. So do not, make sure you're switching it off. Don't use ordinary copper wires as for fuse. Remember that fuse wire should melt at 200 degrees Celsius. Normal copper wire has the melting point of 1080 degrees Celsius. So, copper wire, normal, ordinary copper wire, you cannot use. Don't use. Now, what are the do's? Ensure all appliances are earthed properly. Ensure MCB and switches are connected to the live wire, so that in case if there is overheating, overloading, okay, it trips. Ensure proper insulation of wires. Ensure to switch off gadgets and take out the plug from the socket instead of using a remote and putting things on standby. All right, children. So if you want to have the optimum or the best output, okay, appliances have been rated. What does this rating exactly mean? So that you have the optimum output, energy is not wasted, electricity is not wasted, and you don't have to pay extra for it. Okay, so you must have seen a label or a sticker put up on fridges and ovens that it's a 5-star rating and stuff like that. Okay, that label may give you a lot of information. So here are a few. Okay, just three that I brought for you. Okay, so a fluorescent tube will have the power rating of 40 watts. Okay, and a voltage of 220 watts, which is normally there, in if supplying through is being supplied to us through our main circuits, and a daily use of 5 hours will give you a good or a lesser a proper output. If you use it more than that, there could be a possibility of the circuit getting heated. A fan, 60 watt, 220 volts, and it can work for 15 hours. A geyser, 2000 watts. Children, how much of consumption of electricity? 220 volts of 220 volts rating and a decent 1.5 hours of usage. Okay, so this is how you see the power rating of appliances put on these kind of electric appliances. Did you know the energy consumed when in our houses or shops or in our houses or shops or factories, etc., is measured in kilowatt hour? Yes, we know. Yeah, when we spoke about this while speaking about energy meters. Okay, now kilowatt hour is the unit in which the consumer pays. Yes, I have explained this as well. So, children, we know quite a bit about electricity, its hazards, and about the appliances and earthing and series circuit and parallel circuit. So, for today, that's all. Thank you, and God bless you all.